That's small stuff. Let's see. So we're looking at Zener diodes. I think I've already got it open. Okay, so what's the primary use of Zener diodes? Regulate what? Voltage, yeah. So their primary use is but normally put in the circuit how? Huh? They're going to be paired, in reverse bias. We put them in the circuit reverse bias. We hook our loads in parallel with the Zener, right? You understand? Or we hook what we're driving on the output of the Zener. Later on, when we get into bipolar transistors, I'll show you how to increase the current drive. So these guys here maintain a relatively constant output when we reverse bias. And then we talked about breakdown, talked about the IZK, IZT, and IZM. Are you okay there? So what's IZK? Well, there it is right there. What's IZK? That's the current that flows through when it operates right at the knee, right after it gets out of the knee. We call it IZK. IZT, that's where the Zener voltage is set. That's when it's most stable. And IZM, this is the maximum voltage we need to let go through the Zener. We're going to burn it up. And we calculate it by taking the power rating and divide it by the Zener voltage. And we're looking at the 4700 series of Zeners, because that's the one we're using, but there's all kind of guys out there. And then we looked at the data sheet. And then we looked at a basic circuit. Now what we have to understand that on the basic circuit, we got to have a series resistor. What's the function of the series resistor? Generically, we call that RS, but it could be just about anything. On printed circuit boards, we label these things R. So Zeners are labeled Z. Resistors are labeled R. When they label them on that. So this might be R53 on a printed circuit board. But generically, when we talk about these, we'll give them generic designators. Now, what's the function of that RS right there? Yeah, but it's got a function. I mean, I could put a 50,000 ohm resistor in there, and it would definitely protect it, but it would not be considered RS because the Zener couldn't regulate with that resistor in there. So what's the function of that resistor right there? Well, yeah, okay.
Basically saying the same thing, but
well, not really, but that would be a little closer. The purpose of RS is to drop the difference between the unregulated and the regulated. That's its function in life. So it's in there to drop the difference between the unregulated voltage and the Zener voltage. That's its function in life. And of course, you're right when it said it's in there to protect the Zener. That's a fact, but its function in that circuit. So I could use a lot of things to protect the Zener, right? So what it's doing is it's sitting there. So on this side we have unregulated. On this side we have regulated. So this guy right here, we've got to size that thing to be able to support the load and support the Zener current, right? You understand that? So it's critical when we size that thing to make the Zener operate above what we call the knee. So we got to operate the Zener above this point right here. What we're trying to do is we're trying to move it toward IZT. Are we going to hit IZT? Highly unlikely, but we can. So we start off by calculating what would put it at the knee, right? And then we're going to go to the next lower size to move it further down that slope or above the knee. Yeah, low current applications. So, but we do have current amplifiers that we'll get in later on. So we can use the Zener as the voltage reference and then add to a current amplifier, right? Does that make sense? and we'll see that later on. I think I showed y'all the prints of the 7800 series of regulators. Okay. Any voltage applied to the Zener that is above voltage ZK will be a short circuit. A resistor is connected in series with the Zener called RS. It is required to do what? Drop the difference between the unregulated voltage and the regulated voltage. And of course, it's critical to the operation of the circuit. If we choose a side that's too small, it's going to burn the Zener up. If we choose a size that's too big, then the Zener won't regulate, right? Y'all understand that? So when we look at the whole circuit, if we came over here and did it, we're going to hook this up and we're going to try to design one here in a second. So what do we got? We got outbound power coming in, and then what's the first thing we're going to hit? In a linear power supply. What's most likely the first thing we're going to hit? Guys, we've been doing it all semester. What's the first thing you do what's the first thing we're going to hit? Starts with a T. Yeah. So the first thing we're going to hit is we're going to hit the transformer. And what's the function of the transformer? To get you what you need on the output. So you size it to get your voltage you need. Of course, we're going to step down. And then what's the next thing we have? Well, we called it rectifiers. Yeah, we're going to have rectifiers. This is set up for full wave, so we'll do a full wave rectifier. And that's what we got up here anyway. And we're going to do a positive supply. And we're going to consider this to be common. Of course, as soon as we hook our scope up, it becomes a true ground, right? Okay, then what comes next? Not a resistor, filter. So we'll come up here, we'll put our filter right here, and it's going to be polarized, so this one right here, we'd put that, and then we're going to come in, and what's going to be next? The Zener, okay? So normally we'll draw this like this because of the way we take the output. So we'll put our series resistor right there. Our Zener's going to be right there. Reverse biased, right? And then this is going to turn into the output of our power supply right here. And that's going to be regulated as long as we design it right. So what we got right here, all this would be before that, right? You understand that? But all we're going to do right now is just look at the Zener basic function of this. So this would be RS, or R53, and this would be Z something. We'll just call it ZD right now. Diodes are labeled D, so they might be D1, D2, D3, and D4. Capacitors are labeled C. Transformers are labeled what? T. Now, of course, what we're probably going to have is we're either going to have a fuse over here or a fuse over here, and the most popular is to put the fuse right there. Somebody asked if it was okay to fuse both sides, and yes, it is. You can see that every once in a while. You don't see it that often, but you see it every once in a while because the more stuff they put into it, the more expensive it is, right? We might have some type of display, you know, we might have something, we might, of course, if it's a power supply, what else we're probably going to have on the primary side? Yeah, we're going to have some fuse. So normally what we would have is we'd come over here and we'd put this in. And then we'd come through and we'd have a switch. And then we'd have a fuse. You know. So this would be pretty much a pretty good power supply. And over here we might could put the trainer put all the LEDs over on this side. But you could put an indicator. So right now I'll just put a light bulb right there. That indicates when we have it what. on or off. That's very, very common. Could be a little neon bulbs. Neon bulbs work great. If we put a neon bulb, we wouldn't have to put a resistor in it. But if we put an LED, we'll look at that later on, show you how y'all could actually put an LED. Okay. Everybody okay? Any questions? I'm going to erase all this up here and just move down to here. You know, but I wanted to draw the whole setup of where we're at right now. So, first of all, we're going to come over here, and if we're going to design a power supply, what's some of the things I would need to know? What's the function of the power supply? To the loads. So, what would we need to know about? We would need to know about the loads, right? What's two things we probably need to know about the loads? Or current, and that's good. First of all, we need to know volts. And watts, we would when we calculate our Zener and everything, we use current. But you're right, we could use watts. But remember, I is equal to what? What's the main formula? I is equal to P over V. Yeah, we're doing it relative to power. So if your load is rated in watts, we have to know the current to design the Zener. But if you know the watts of the load, it's very easy to get it over to watt. So we'll just put IL right here. We need to know these two things. And then, so what do we want? So let's look up one of our Zeners and what voltage y'all want to use. 24 volts?
Yes.
Let's see if we got, we got a 12.6 volt transformer. We can't get that out. We're going to wire this up.
Oh.
I've got a 1N4733 up there, so let's look up that. Hey. So where's the data sheet? Where y'all gonna look it up at? Be on Blackboard, right? Go to where? Data sheets. And of course, ours is labeled 1N47XX because there's quite a few versions of the 4700 series. We're going to use 4733. Yeah. So what's the Zener voltage on this? I think it's an A. Huh? It doesn't make any difference if it's A or a. But yeah, mine's an A. So this is 5 point. So VZ is 5.1. So how much of the transformer we're going to use? Are we going to use the full 12.6, or we're going to use the full? Are we going to use 6.3? Yeah, we're going to use 6.3 because if we use 12, the wattage of that resistor would have to be real big because it'd have to drop a lot of voltage. So we're going to use 6.3. Now our transformer is kind of weird. So Alabama Power, I mean, what does NEC say about this 120 volts? Anybody know? So NEC, when it gives what they call the optimal voltage, they call it 120 volts. And but that can vary, and it could still be legal, plus or minus 10%. So that means it could be as high as 132 volts, or it could be as low as 108 volts. When I look at my transformer, it says the primary is 110 volts, and it says at the output, I get 12.6, but we're going to get 6.3 because we're only going to use 1/2 of it. So what's the division ratio there of the transformer? Or you could do it this way. It's going to be the same division. So we're going from 10 to 110 to 6.3. So, don't know. Sounds right. So the division ratio, we take the input voltage, we divide it by the output voltage, right? And this will give us our ratio. So what would that be?
I got about
19 point what? 0.8. Okay. What's that? I'm not, I don't have my calculator. You're doing this for me. I'm just listening. Oh, I mean 110. I'm sorry. No, the transformer is rated to give us 6.3 volts at 110 volts. So the transformers, and of course, that's just what they rated. It's just like if you go out and buy an incandescent light bulb, it's rated at 115 volts. So they rate them, but it's still well within the limits of what Alabama Power. So they have to rate it at they have to rate it at something, and most of the time they do it so it comes out even. So a 100-watt light bulb at 115 volts, because they would rather say 100. Understand, instead of saying 102 watts or 104 watts at 120 volts. Okay, does that make sense? So here we got 110. Excuse me, that's where I made the problem. What we're trying to do is figure out if we know the division ratio of the transformer, we'll know what we'll get at 120 volts. Yeah, it is 110. I just said. So 17.5. Okay, so that's our division ratio. Okay, so what we're doing is we're putting 120 volts on this. Well, we can put anywhere between what? 132 and 108. Anywhere between that is going to be legal. So if I design it around those ranges, that means it'll work everywhere in the state of Alabama, in the United States, right? You understand that? Because not unless there is a major problem. And if they got up above 132 volts and everything in your house is going to be burning up, if they get down below 108, then hardly nothing's going to work. So this is pretty much well guaranteed unless there's a problem. So y'all follow me so far? So the 47, and of course this is a 1 watt Zener. All those Zeners are 1 watt. So 5.1 volts, 1 watt. Okay, so what do we need to do now? We need the size RS. What do we need to know about RS? Well, we need to know our load. So let's use 30 milliamps, because that I know I have the resistors for that. And of course now our voltage on our load would be, it would be a 5-volt load or around there, right? So we chose a 5.1 volt Zener, which is going to be good. The Zener voltage is a little higher, which is what we really want. Okay guys, what do I need to do next? We're trying to size what? RS. So what are we going to do? We're just going to start picking resistors until it works. Huh? Well, we're not, power's our last thing we're going to worry about. We got to size that resistor. That resistor's in ohms. We'll get an ohms, and then we'll get the power for the resistor for that ohms, right? Somebody tell me what we need to do. What do we need to know? Okay, so it's got to be some derivative of R is equal to V over I. We went over through that, right? R equals V over I. So now we got to figure out what V it's got to drop and what I it's got to conduct, right? So that's the formula right there. So you got to say, okay, what's that sucker got to drop? It's got two voltages. It's got a voltage range it's going to have to drop. Okay, well, first of all, we're putting 6.3 volts in. We're going to use the center voltage to calculate that, right? So what I'm going to do is I'm going to say V out. In fact, we don't even need to use 120. I'm going to use 132 to get the maximum voltage, because 120 is between that range, right? You understand? I'm going to say, okay, so V secondary would be equal to 132 divided by 17.5. And down here, I'm going to say V out secondary minimum. So this right here is max, right? This is going to be equal to 108 divided by 17.5. So y'all see what I'm doing? Does that make sense? So now we know our minimum voltage and we know our maximum voltage. So what do we get for the first one? So V secondary max would be equal to what? 7.6. And V secondary minimum would be what? Was that 6.2? Are we okay? Now what's the next thing I need to do? Somebody help me? Huh? Yeah, we need DC out. Okay, so we need a minimum and maximum. So what we need to do is we need to calculate the DC voltages right there. So what's the next thing I need to do? First of all, I need to get V peak. So this is right down the line of what we've been doing, right? And we'll calculate V peak out minimum. I hope all this works out. So what we got for V peak out maximum? Okay, 10.7. And what do we get for minimum? Okay, so what do we need to do now? Okay, so what we got over here is we've got a 1,000 microfarad capacitor at 50 volts. So we're going to be fine, 50 volts. We're not even going to get approached that, right? So we're not going to blow this thing up. We got a video if you want to watch it get blown up. We had a guy in our class, he was taking, used to his motor controls. They had benches out there that had three-phase, two-way three-phase down there. And now it's a lot different. I guess you could still do it. And had a circuit breaker there. So that's what you did. That was your disconnect with the circuit breaker. Well, a guy named, I can't remember his name now, guy. I remember the first name, Steve. And we heard something going, boom, boom. And old Steve was taking electrolytic capacitors and putting them across the three-phase line, 208 volts, and turning on that breaker and blowing them things up. And over in 250, y'all ever been in 250 before they took it away from us? It used to be a physics lab. And so they have gas outlets on the table for physics, like a chemistry lab. And it's coming down the hall, we heard something go, you know, Steve was in there with his cigarette lighter holding on one of those things. So he was that kind of guy. You had to watch Steve. So that was the kind of guy you don't want to work with. You want to talk about, but you don't want. Same guy too. Well, he made us do some stuff. We had the gas. We didn't use the gas, so we had the gas turned off in that lab. Well, I wish I could remember Steve's last name. So, I mean, he was 208 volts on a little electrolytic capacitor. You're talking about something blowing up. Nowadays, everybody be running because they think it was gunshots. Okay, guys, what's the next thing we need to do? Yeah, let's get DC out. First of all, we need to get, so what's our DC out going to be? What's that? No, this is, yeah, so let's go ahead and do that. So we're going to use a full wave bridge. So V peak out, this is out. This is actually V peak. V peak out would be equal minus 1.4. Thank you. And why 1.4? Because we're using a bridge. Yeah. No, 10.7 minus 1.4.
Oh, that part. Oh,
yeah. Set 9.3, and then 8.8 minus 1.4. Okay. So these are the voltages that we're going to work with. Okay, guys, what do we do next? No. No. That's back before we added this. As soon as we add these, those 2 V peak over pi and that V peak over phi, those formulas are no longer valid. Because it never goes to 0. That only works with an alternation. That pi only works with that alternation, right? You understand that? So those formulas are out, and that's a standard mistake people make with these power supplies, because we've been dealing with that 2 V peak over pi for full wave and V peak over pi for half wave, and all of a sudden we throw a capacitor in there, and as soon as I put this capacitor in there, those formulas are no good. So DC out or V out is going to be equal to what? Yeah, I mean, we're charging that sucker up to V peak, and as soon as it drops down to V peak, it starts dropping down, right? You understand? And then it charges up on the next alternation. We never go to 0. So the only difference between V peak and my output voltage is that dang ripple voltage. So the formula is what? Yeah, it's VP out minus V ripple peak peak over 2. It's supposed to be a minus. So we know V peak out. V peak out is either going to be 9.3 or it's going to be 7.4. So what we need to do is calculate the ripple. So full wave. Alabama Power. Yeah, we're plugging this. We got a transformer up here. I mean, this is the circuit we're working on. I mean, I got my camera plugged in, so let me bring my camera in. So we're going to wire it up all the way. Of course, y'all are using the output of the transformer, the trainer. And I like to hook this up. When I hook them up, I like to hook them up and actually show y'all the whole thing. 1,000 microfarad. And we're doing this for a 30 milliamp load. It took me trying to figure out one that would work. Come on. Okay, what's happened to? I hate this thing. There we go. So here's the circuit. So here's my transformer. Of course, it's rated at 110 volts. Nope, wrong transformer. So it's rated at 110 volts, 60 cycles, and it's rated at 1 amp. So we're not going to run this thing near what we need to run. 12.6 volt CT at 1 amp, but that's at 110 volts. Odds are the transformer that we're using in the trainer is rated at 110 volts too. What did I just see? Over here. No, it's rated at 120 volts. Then we got our bridge. Okay, so then we got our bridge rectifier right here. I couldn't find my other one, so I just made one of out of 4 diodes. And we got a 1K load. This is the one we had the other day, so it's got a 1K load out there. But this is where we're going to come in and we're going to hook up our actual load. So this is where we're at right now. So transformer, rectifier, and then of course filter. So we're going to make it a positive. So here's my common anodes going out here. So I'm going to put my capacitor in there in this direction. And we got a thing called a variac over there. Now, when we do our Zener power supply, we're going to hook it up to a DC power supply. Because what we're going to do is we're going to set a minimum voltage and a maximum voltage. Y'all understand that? So we can actually see the thing regulate. Here, that would kind of be type of a dynamic thing. And it don't want to focus in anymore. There we go. Good job. So there it is. Okay, so we got 30 milliamps of load. Y'all got y'all's formula sheet, right? Got 30 milliamps of load. We've got a 1,000 microfarad capacitor and 120 hertz. What y'all got for y'all's ripple voltages? .03, right? Divided by open this 120 times Um, so what you got? I got 250. I did it twice through, so it's like, so we're going to just ignore that. So what am I going to use for my maximum voltage? So my maximum voltage will come up here, just use 9.3. And then for my minimum voltage, we'll use 7.4. We'd probably use 9.4 anyway, but 250 millivolts out of that. 7.2 something, but that's okay. Okay, so what do we need to do now? So what voltage does my resistor have to drop? What's the maximum voltage it's going to have to drop? Somebody help me. Oh, dang it. Won't let me erase that stuff. Okay, guys, what's the maximum voltage that resistor will have to drop? We're just kind of, what's the maximum voltage RS would have to drop? So how'd you come up with that? Yeah, good. So VR max is going to be equal to this minus this according to Kirchhoff's law, right? You understand that? So what we got? I'm listening. 4.2 volts. VR minimum, what's the minimum voltage you'll have to drop? 2.3. Now we know V. What are we going to use? Are we going to use the minimum voltage or the maximum voltage? So we're working on this formula right here. So R is equal to V over I. What we're trying to do is figure out which V we're going to use. We're going to use the minimum. Why? Because the minimum is going to put it toward the knee. If it goes up to maximum, the current's going to go up, and it's going to move it away from the knee, right? You understand that? So yeah, we're going to use the minimum voltage. Okay. So RS would be equal to what? 2.3. And what current are we going to use? Well, I know it's got the load current, right? It's got to handle the load current. So the load current is going to be 50 milliamps. Okay. But we've also got to have some Zener current. So if I calculate it to drop all that voltage at 30 milliamps, then there would be no Zener current. We got to have Zener current, right? So my resistor has got to ensure that we always have current flow through that puppy. And then, of course, we got to have current flow through the load, too. So we're going to have to size that resistor so it's going to conduct 30 milliamps plus some Zener current that we've got to guarantee. What Zener current do we have to guarantee? We got to guarantee IZK. Y'all understand that? And of course, we're going to move it away from IZK because we're going to round this resistor down. So it's going to be 30 milli plus what's IZK for this diode? What's IZK? IZK. You gave me ohms, and I'm looking for current. What's that? 1 milliamp? Or is it 0.1 milliamp? Huh? 1 milliamp? Okay, you're right. I'm sorry. So 1 milliamp. So we're going to size a resistor that'll drop 2.3 volts at 31 milliamps. (2.3 divided 2.3 divided by 0.031. Oh my goodness. Is that 30 milliamps? What y'all got? Yeah, we're going to do something. Huh? That's what I got too. What do we get at, what do y'all get at 25 milliamps? And it still won't work. Y'all know what I'm doing? We don't have a 74 ohm resistor. We got a pod. We can set any resistor we want, but because I think what would be the next standard 68 ohms, and then that probably wouldn't be good. So we'll probably have to go down one more. Y'all know where the standard resistor chart is, right? Let's do 20 milliamps. Now the only reason we're changing this is because of the size resistors we have available to us. And it's going to be close, but we'll use it anyway. So what size one we got? So down here we'll say 2.3 divided by 21 milliamps, right? So what do y'all get? 109.5. So that means we'll use a 100 ohm resistor. What would the tolerance be on that? 5%? We're going to be fine. So we got a 5% resistor, plus or minus 5%. So I'm going to take 100, I'm going to multiply by 1.05. So it could be 105 ohms. And we need 109. So what we do is we check the tolerance and make sure the tolerance is less than this. We don't have to check the low tolerance. We need to check the high tolerance, right? Y'all understand? Because the bigger the resistor, the more it moves toward the knee. So if it's on the low side, that's even better. But if it comes up above this, then what does that mean? That means it'll go out of regulation, right? It'll go up in the knee. Okay. So we got a 100 ohm resistor. Okay. There's one thing I wanted to show y'all first before we hook this circuit up. It's almost time for break anyway. What I did, I'm gonna take the resistor out, and I had to put a resistor in it because power supplies don't like to be unloaded, right? DC power supplies don't like to be unloaded. So what I'm gonna do is let me get my scope probe over here and let y'all show y'all what's going on. And then because we talked about this the other night. A lot of people want to know why do we have these unregulated power supplies? So I'm gonna make this my ground. I'm gonna make this my. And then of course I got a resistor there. And of course, there's our DC. Let me put it on, right now I got it on AC couple. So DC. Okay. And it's snaking across there, so what does that mean? That means I need to trigger my scope, right? Okay, so there's my DC. And you can see if I take the resistor out, it goes crazy. So you got to load these things, because if you don't, then the diodes are not going to forward bias because they can't get that 0.6 of a volt difference. I mean, that 0.7 of a volt difference, right? Okay. So what I'm going to do is I'm going to come up here. I've got a little 12-volt motor right here. And I'm going to put this little DC motor across the thing and find my other lead. So I got it hooked up across the positive and the negative. It's running against my scope probe. And of course the thing does what? I mean, it runs fine. So this guy here don't care. But what happens is that when the pulse drops down, the motor regenerates back into the system. So when I come over and look at my scope, you see it's no longer going. Now, DC motors are notorious for being extremely noisy. So this is what we got without the motor. This is what we got with the motor.
That would get worse.
Huh?
It would get worse.
No, it'd be the same. The resistor, I only put the resistor in there so we could see the halfway. But that's not always being regenerated by the motor. And then of course it actually does what? It actually turns it into a DC. Now it's not beautiful DC, but it's still DC. This motor don't care if it's halfway. They don't care if it's full wave. All it's doing is looking at that average voltage that we're talking about, that 12. Okay, so what we're going to do is we're going to hook up our power supply. So I got my Zener. So here's my Zener. Okay. And let me turn this off. I'll hook this up. I'm going to take off the 1K. We're going to load it with 100 ohm, right? Well, we're going to use a 100 ohm series drop-in resistor. So what I'm going to do, here's the DC output of my bridge. Okay. And we're going to come over here and take our capacitor, and we're going to put it all the way across the thing if my leads will fit. If it don't, then not. So we're honoring the polarity. So I don't want to put it in. This is going to be our negative side. This is our positive side. So I'm going to come over here and put my it won't fit. So I'm going to have to use some wires. One of my transformer leads pulled out. Hopefully it don't break. Then I'm going to put a what? I'll put my resistor. So we got a 100 ohm resistor. Then what comes next? Now then my Zener. And then we'll come from the negative side here to the negative side here. And then of course we'll put our load in parallel with this thing. But it should regulate. Let's calculate the power on the Zener. So we should be able to handle the thing if the load is disconnected. So what? Make sure we're not going to burn our Zener up. Somebody tell me what I need to do. So we know power, one of our main power formulas is power is equal to P times V. Sorry. All right. Power is equal to, so we know power is equal to what? V times I. So what voltage are we going to use? Calculate the power of the Zener, and also we need to calculate the power of the resistor. I've got a half watt resistor, so I know it's going to be okay. So how do we calculate the power of the resistor? I'm running out of space to write, guys. Okay, guys. Power of the resistor. Well, let's go back and so y'all got the information written down. So power of the resistor is easier to use. It's easy to use V squared over R. So I know my power of my resistor. I know I'm going to put 100 ohms down there because that's the size. So when we calculate the power of the resistor, and this is a problem people have, they use the calculator. You don't use the calculator. You use what? What you put in there. Okay. And what voltage are we going to use? When is it going to consume the most power? When it's dropping the low voltage or the high voltage? It's got to drop. That resistor's got to drop anywhere from 2.3. What's the lowest voltage it's going to drop? 2.3. Is that what we calculated? We'll go back. Yeah, 2.3. It's going to either drop. It's either going to drop 4.2 or 2.3. When's it going to get the hottest? 4.3. Okay, so when we calculate the power of the resistor, we're going to use the maximum voltage it's going to drop. That's why we have to get both of these. One of them we use to calculate the resistor. The other one we're going to use to calculate the power. So I would say what? 4.3 squared. So what's the power of the resistor? What power resistor we need? We need 185, 185 milliwatts. We got a half watt, so we're okay. But we could have used a quarter watt there, been fine. I mean, that's almost double the power. Power of the Zener. We got to make sure we're not going to make this thing dissipate more than more than 1 watt. These are 1 watt Zeners. So I'm going to take this again right here. I'm going to take 4.3. I'm going to divide it by 100. And then I'm going to multiply that by 5.1. So we don't have the load in there. So this is the maximum current right here, right? Y'all understand that? This is the maximum current that's going to flow through the Zener. If we do what? If we pull the load out of it. So what I did is I calculated the maximum current through the resistor. And it's a series circuit right now. It's no parallel, right? You understand? As soon as I put that resistor in there, it's going to take some of the current away from the Zener. So what we got? So 4.3, so we're calculating the voltage and divided by 100. That's the current flow in the Zener times 5.1. Yeah, 219. We got a 1 watt Zener. Are we okay? Okay. So we should be able to fire this puppy up. We should be able to get our voltmeter and put it across this. And it should measure fairly close to 5.1 volts. This is an A, so it's a, my meter don't have, my stands broke off my meter. And then when we get back off break, we'll figure out how to put a load on it. And this was basically what you're going to do in the lab. But instead of using AC, what you're going to do is you're going to use DC so you can adjust the unregulated to a minimum voltage at a maximum voltage, right? So that's what we would do with the regulator when we specify it anyway. It's too hard to put AC on that thing. So here's my camera. I'll just hold up. I'm going to turn this thing back on. So double check. Okay, I got negative, faster, positive on the positive, negative on the negative. Got my resistor, got my zener, in there, reverse bias. By the way, it wouldn't hurt the zener if you put it in there forward bias. Instead of dropping the 5.1, it would drop about 7/10 of a volt, right? I need safety glasses though. Okay, so I got my meter on volts, 20 volt scale. Probably just blew my fuse. Let's see. It's alright, it's measuring what? 5.3 volts. And I hooked my meter leads up backwards. It's actually a positive 5.3. Both of my jumpers are red, so. So what we'll do when we get back off a break is we got 5.3 volts, which is well within the 5%, right? So you okay? So we designed and built a Zener power supply from what? From scratch. Okay guys, y'all take a break. And what we're going to do, and what y'all are going to do when y'all do this lab, the next lab we'll do is, once you do your power supplies, then the next lab we'll do Zener. We'll do Zener. You're basically going to have to do about what we did. But instead of all that stuff with the AC, what we're going to do with Zener lab is you're going to hook it up to your DC, your variable DC power supplies, and you're going to bring it up to the minimum voltage and the maximum voltage. So you're actually going to put a solid DC on there, and that way you can do what? You can measure and make sure everything's okay. And that's probably what we would do if I was an engineer. If I designed one to be able to regulate between them voltages, to check it out, I would actually put true DC voltages on it. And that's the way we would run it. Okay, so what do we got so far? So we got our watt. We'll block it up to here. So I've got my watt. I've got my AC, and then I've got my watt. I've got my transformer, right? And then I've got my watt. I got my filter. Okay. And then what we got now, then we come out of this, and then I got my RS, and I've got my Zener. Put in there reverse bias, so this is our positive. Okay, so we're going to hook our load where? In parallel with the Zener. But what I want to do is I want to put a load on there that I have the ability to vary. Okay. So what device allows us the ability to adjust the current? Yeah, rheostat. You very seldom see rheostats anymore. What you do is you see pots that are wired to act like a rheostat. So how do we wire a pot to act like a rheostat? Anybody know? You connect the wiper to one of the ends. That's all there is. Now it's a rheostat. Of course, the problem is I'm not going to do that because that's going to be very dangerous. Because if I accidentally turn my rheostat down, we're going to burn some stuff up, right? So if I bring this down to here, we would have a short circuit. Probably burn up our little resistor. And then plus we need to be able to measure the current. So what we're going to do is we're going to come up here and we're going to put a resistor. And we're going to use a very convenient resistor. We're going to use a 100 ohm resistor. So let's make sure we're using this. So the maximum voltage we should ever get across this, when I adjust this to 0 ohms, should be 5.3 volts around there. So I'm going to make sure I got a half watt resistor. So that's 5.3 volts squared divided by 100. What does that come up and give me? Milliwatts. We okay, milliwatt? It's a half watt resistor. All I did was just make sure if I do turn that pot down to 0, we don't want it to burn up that resistor, right? So we check the power of the resistor, and that a lot of people won't do that. They'll just grab a resistor and they'll stick it in, and they'll wonder why it burns up on them because they didn't do what? They didn't calculate the wattage. So resistors are rated in two primary things. They're rated in what? Ohms and watts. Of course, the ohms have a tolerance. A lot of people want to say three things, but normally when we talk about what it's rated in, we know every electronic device I would use tolerance. So when we talk about what they're rated in, we're talking about what else they're rated in, right? Okay, so what are we going to do? Now what I can do to measure my current is I can just measure the voltage drop across that 100 ohm resistor. And then we'll say, well, I, the load, because it is the load, all this out here is the load, would be equal to what? VR minus 1 over 100. Are we okay? Okay, so what I need to do is get another meter. Take all my meters. Yeah, I figured the controller for the little Mitsubishi robot. Set the pot in the center. This is a 10K pot, so we can go anywhere from, so we can set our resistance anywhere from 10K down to 0, right, which would be a rheostat. When we give the size of a pot, we give the maximum size that you can adjust it. So what's the function of a pot? It's to give us a voltage. So what we do is we use that as a voltage divider. Y'all learned voltage dividers back in DC, but it's a variable voltage divider. So what we're doing is we're changing the ratio between two resistors, and we're taking the output in the center of those, which is pretty neat. If we come over here and hook this up, so we're going to go across the Zener. We're going to go in parallel with the Zener. Okay. So I'm going to put here on that one. Oops. And I got my pot set in the center. And I'm going to put wiper 2 up there, and then I'm going to come over here, because this is not, I'm not going to put this across because we got to put this in the 100 ohm resistor in series, right? Oh my goodness. Huh? No, it's got, it looks like it's been soldered into something before. It's the right resistor, but I wouldn't been able to get it down inside the hose. Still can't. I need to cut it off. What's the color code for 100 ohm? Brown, black, brown. Right. And don't be surprised if you see color code questions on your test, by the way. Okay, so here's my pot. I've got my wiper connected to one side. I've got the other side connected to the top of my resistor, and then I've got my common on the other side. And then we'll use this meter. We're going to use this meter to measure our voltage. And we'll use our other meter to measure our current. And I need a set of, so what we're going to do to measure our current is what? We're just going to hook it across that resistor, and we're going to measure it in direct. And I got so much stuff over here. Normally when I get all this stuff up here, I'll get my meters messed up. So luckily they're different colors this time. So the red meter is measuring the voltage drop across the zener. We're going to see if it's going to be able to regulate. The yellow meter is going to measure the voltage drop across the 100 ohm resistor. And let's fire the puppy up. Got it on volts, volts, DC, volts, DC. Turn this meter on. So what's my current flow right now? Somebody tell me. So that's 96 milli divided by 100 ohms. So what's the current flow through there? What's that? 960 microns. Okay, so what I'm gonna do is I'm gonna start doing this. Notice the current. So what would be 30? What would it drop for 30 milliamps? I'm sorry, 20 milliamps. We did for 20. We changed it to 20, right? Because we didn't have a 74 ohm resistor. So this is DC. I mean, this is right down the line. You know, everything we've done is we've applied what y'all learned in what? DC. Right? You understand that? But the AC stuff, we just learned a few new formulas, but what we're doing now. So I want to know what that meter will read if I'm doing 20 milliamps. What's it going to measure? What should it measure? 200 micro? We okay? Now let's watch this guy. As long as it stays above 5.1, then our power supply is beautiful. Didn't even move, did it? Yeah. Now let's go down and let's load it more than we designed it around. Let's see when it actually starts. So there's 500, 600, and of course it just did what? And now we just went out of regulation. So what just happened is I pulled too much current. So now my 100 ohm resistor is dropping the voltage and it's gone back up in the watt. It's gone back up into the knee. See that right there? So that's a really good supply. So we designed it for 20, and we actually got that would be 100 milliamps, right? Or 1 milliamp. I'm sorry, 20. Be 100 milliamps. So we actually got 100 milliamps through that resistor, and you can see exactly where it goes out of regulation. See, look there. Can you see what it's doing? And that's the best I can do right there, guys. But this is all the way unregulated. So it'll probably take a little while for the Zener to cool off. So if I was to come over here and look at the input would actually be varying, right? You understand? This guy here is, so let's look at this with an oscilloscope, make sure we keep our ground. Of course, with that 1,000 microfarad capacitor, so what we're going to do is we're going to put this on AC. So we're going to change this over to AC coupling so we can block the DC, right? Okay. And then we can come over here and we can see what's going on with our ripple voltage. Oops, dang it, Rich. I'm hitting the wrong button. This is the button I'm working. Oh, that 1,000, that 1,000 microfarad capacitor is doing a really good job. All right, you can see it moves a little bit. So what do we calculate for our ripple voltage? What, 200 microvolts?
Yeah.
No, that's yeah. Because we're getting 20, 40, 60, 80. Sorry, 20, 40, 60, about 70. That's about 70. That's millivolts. So you can change right there. Yeah, so I don't know if you can see it dropping down. So we've got a really good filter. We might, huh? For our ripple voltage? 20? Well, we got millivolts there, guys. We got, that's millivolts. So yeah, we've got 10, 20, 30, 40, 50, 60, 70, 80, about 85. We calculated 120 something, right? Not bad. That capacitor's doing a really, really good job. That's 1,000 microfarad. I still got to bring my power supply in. I can't remember how much I think I've got in mind. So this is what we're going to do. So what we're going to do is we're going to come in, and y'all see how we load the thing. And what are we doing this for? Of course, and we'll use, I think we're using a 100 ohm resistor on the layout. We're going to put that in series with a 10K pot, and that way we can do what? We can vary the load current. And we're getting almost 100 milliamps out of the thing before it goes out of regulation. Now the biggest problem with Zeners is just that. We can't get a lot of current out of that thing. But what we'll find out later on is that we can use a bipolar transistor for a current amplifier. And we'll use the output of the Zener as the reference voltage for the transistor, and basically you can make these things get about whatever you need out of them. No load, full load, we already talked about that, went over there, percent regulation. What we do on percent regulation, now, we call it percent error. So when we do your test grades, how do we do your test grades? How do we come up with those percentages? Huh? Well, it's how many you got right divided by the number. But the actual formula for calculating percent oops. I think it's on y'all's data sheet. Can y'all see what I mean, or your formula sheet? Can you see the one for calculating percent regulation? By using the difference of the Zener voltage at minimum and maximum load, and then dividing the difference by the no load Zener voltage. So what we would do is we would come over here and we would take, well, let's make up something. So let's say when we put maximum load over there, it measured 5.1. And then minimum load, it measured 5.4. And what's it supposed to be? It unloaded, it measured what? 5.3. So what we would do is we'd come up here and take these two numbers. This is what it measured unloaded, and this is what it measured full loaded. And I would take the big one, which is 5.4. I would subtract a little from it, 5.1, and then I would divide it by what I want it to be. Of course, ours would actually be 5.1. And then we'll multiply that times 100 because this is in a percentage. So what would we get? What would be our percentage of regulation for a Zener that had this guy right here? Y'all are not going to use 1,000 microfarads. Y'all are going to use 100 microfarads, so y'all have a bigger suite. So 5.4 minus 5.1 divided by 5.3. And then times 100. 5.7%. So it's going to regulate within 5.7%. Did y'all get the same thing? No. Or you'd say it's going to regulate. So it's going to, our regulation is going to be within that, right? So that's really, that's not bad. So this is what y'all going to do. You're going to calculate. You're going to build your power supply. You're going to ask for a Zener. So I'm going to give you. You'll figure out which one of those 4,700 Zeners you're going to use. You'll ask for the Zener. Then you'll calculate RS. You'll ask for that resistance. Hopefully it works out. It should. We've been doing it for a long time. So a resistor that we have. Then you're going to hook it under load, right? You understand. You're going to use a pot and a resistor. You're going to put it under load. You're going to adjust it. You're going to see if it works. You're going to adjust it within the design parameters. And then you're going to give me the percent regulation. That's right. So we basically did the lab tonight, except we did ours with the true transformer. We didn't do the limitations or anything like that that y'all going to have, but we did basically exactly the same thing. So some of y'all about ready to do that too, right? And then, so we won't have, we won't use the transformer, we won't use the filter, we're going to use the power supply that are in the trainer. And that way we can adjust it for our minimum voltage and our maximum voltage and actually watch the thing work. It's just like amplifiers. If you work in stereo amplifiers, then I don't know if y'all have ever seen audio before, but you can't hardly troubleshoot audio because it's all over. So what you get is you get you a function generator, which outputs a sine wave, right? You understand? And then what do? Then you put that in and you can measure. Now you can measure what in and out, and you can see the gain. You can change the frequency to make sure the frequency response is what it's supposed to do. You know, make sure that it does the range of frequencies that it's supposed to do. You know, so if I say something's rated has a certain bandwidth, then they're not going to have the actual signal on there. They're going to put a piece of test equipment on there where they can put out those precise bandwidths, right? You understand and do the meter. So that's what y'all going to do. Y'all going to do like if you were designing this regulator circuit. This is what you would do. You put DC on it and you do what? You take it across the ranges it's supposed to regulate at. And then if it regulates between those ranges, if you hook it up to the rest of your circuit, it was designed correctly. And it's going to work exactly like it's supposed to. Yeah, guys, y'all did a good job. That thing's regulating great. So my resistor's getting pretty warm. Because we're running it way above what we're supposed to be running. Okay, any questions? Y'all ready to go lab? Got a worksheet for seniors, by the way. I'll get that out for y'all to work on during the weekend. I know y'all really love these things on weekends. But it's a Zener worksheet, and it's basically what we did tonight, just to let you see if you can do this. And y'all getting there, guys. Okay, so y'all can go ahead and go to the lab. I'll get the worksheet out and I'll bring it around.